So today we're going to start talking about one of the more recent major advances in relativistic astrophysics, namely the detection of gravitational waves. And we'll talk about it first from a conceptual point of view, and then after intermission, we'll talk about the specific instrument with which this has now been done. The objects we've been talking about so far in this part of the course, the pulsars, the X-ray binaries, the quasars, all followed a kind of very similar historical pattern. In the 1960s, some new phenomenon was discovered, and the reason it was able to be discovered is because new windows of electromagnetic radiation were opened up, radio astronomy, X-ray astronomy, and so forth. And then within 10 years, a basic hypothesis of what these objects actually were had been put forward and more or less established. And over the ensuing decades, more detailed observations were made, more refined ideas were created, and by the turn of the century, in all three of these cases, you had a pretty densely woven web of ideas and observations and theories and a whole set of stories that encompassed and connected all of these different kinds of objects. And so that was the big achievement in this area in the latter part of the 20th century. And now what we're going to do is go on to the 21st century. All of these objects, the pulsars, the X-ray binaries, the quasars, the stellar mass black holes, the supermassive black holes, these all continue to be studied. And the observations refined and so forth. But we're now going to talk about a phenomenon, the first evidence of which was only discovered about 5 years ago. And that is the direct detection of gravitational waves. Now, this is very important from the point of view of understanding relativity. Gravitational waves were one of the very first predictions that Einstein made over a century ago when he developed the theory. And so to have them verified observationally is a great triumph. But it's also very important from the point of view of observational astronomy, because at the end of the 20th century, we had pretty much gone through the entire spectrum of electromagnetic radiation, from low frequency radio waves to radio, microwave, infrared, optical, ultraviolet, X-rays, and high energy gamma rays. Top to bottom, we pretty much explored the whole of the electromagnetic radiation spectrum. And now we get a new kind of radiation. And the expectation is that whenever you start looking at a new kind of radiation, new and exciting objects come to the fore. And so I would say that with respect to studying the gravitational radiation, gravitational waves, we are right now at a comparable point to where we were in the 1960s in terms of radio astronomy and X-ray astronomy. And so there is the hope, indeed the expectation, that many exciting things will come, that we've only just started this new kind of astronomy. So let me remind you about gravitational wave radiation. We talked a little bit about this in the context of the binary pulsar. What happens is you have some mass that's being accelerated. For example, it's in orbit going around in circles, and this generates waves. What's waving? What's waving is the space-time curvature. The amount of curvature is changing periodically in both space and time, and that gives you a wave of space-time curvature. And these waves propagate outward into space at the speed of light, as do electromagnetic waves. They have the effect of changing the sizes and the shapes of objects slightly. That is to say, if all of a sudden, the space-time continuum that you're in is curved more than it was a second ago, then all of the distances, all of the triangles add up to slightly, different numbers of degrees, and all the distances are all slightly changed. And then when the wave passes, or you get back into the trough of the wave, you go back to normal. And then a second later, the curvature changes again. And so objects kind of move back and forth. And we've seen the effect of gravitational waves, although we haven't seen the waves themselves, but we have seen the effect of the gravitational waves on the orbit of the binary pulsar. And you, again, remember how this works. Two neutron stars are in orbit around each other. The orbit's super short, and that orbit is observed to decrease. Here's the observational data from 1975 to 2005. Why is the orbit decreasing? Because gravitational wave radiation is being emitted by this system, and that energy that goes into the gravitational waves is being pulled out of the orbit, and therefore the orbit is marching inward, so that the source of the energy is basically the gravitational potential energy of this orbit. And there's an equation, and you can figure out how long it will take these things to merge with each other. And the answer is some number of tens of millions of years. And that's actually quite short in this context, because the universe is billions of years old. And so we have an example of something in which, first of all, you can observe the effect of the gravitational wave, the shortening of the orbit, and it works out perfectly according to the theory. And according to that very same theory, if it continues to, the orbit continues to shrink at this rate, these two neutron stars will run into each other some number of millions of years in the future. So the question then arises, what happens at the end? What happens when these two objects spiral closer and closer together and eventually merge? So as they get closer, one of the things that happens is that the amount of gravitational wave radiation that's emitted increases. You get more and more radiation. That's because they're getting closer to each other's Schwarzschild radius, and so any relativistic effect is going to increase. That fact, the fact that there's more and more gravitational wave radiation emitted, makes the period decrease even faster, because that's where the energy is coming from to supply these waves. And so as you get closer and closer, this whole process takes off. It's an exponentially increasing thing. So gradually moving together, and then faster and faster and faster until it merges. The frequency of the waves increases. What that means is there's one wave given off every orbit. And so if the orbit gets shorter and faster, more waves are being given off faster. And so the frequency of the waves increases. That's another way of saying that the wavelength of these waves decreases. One wave is emitted per orbit. The orbit's getting shorter, so the waves are coming faster and faster. And because the amount of gravitational wave radiation is increasing, the amplitude of the waves, that is to say the size of the waves, is also increasing. And you can see it on this little diagram here. Out here, when it begins, you have these waves going up and down. And as the two objects approach each other, what happens is the waves come more and more frequently, and the amplitude of the waves increases in an exponentially increasing manner. This is referred to as a chirp, because if you were to have sound waves in which the frequency and the amplitude is increasing, that is to say, the pitch is getting higher and the sound is getting louder. So high-pitched things have high frequencies, high amplitude things are loud, then you would get a sound that sort of sounds like this. That's referred to as a chirp. It's kind of like noises that some birds make. So you get this chirp, and that brings the objects ever closer together, ever faster, and eventually these two objects, whatever they are, will touch and merge. And if it's two neutron stars, then they're going around really fast. And so there's a lot of centrifugal force. And so as they touch each other, merge, they throw some material off into space, but the rest of it combines to make a rapidly rotating, much more massive star. And one of the things about neutron stars is you can't get much more massive without becoming a black hole. And so in many cases, it is likely, for example, with the binary pulsar, it is likely that when they merge, they will end up being a rapidly rotating black hole. If you've got two objects that are black holes already, then the event horizons eventually touch each other, and you end up with a sort of non-spherical Schwarzschild radius. Radius is the wrong word, but you end up with an event horizon that has some weird shape with two singularities inside it. The singularities are driven together, and the result is a rapidly rotating black hole. This is described not by the Schwarzschild metric, but by the so-called Kerr metric, which I think I showed you in passing at some point along the way. You can figure out the masses of the two objects, if you see these waves, by the size of the orbit immediately pre-merger. That is to say, they're going at close to the speed of light. They're traveling a distance 2 pi times the Schwarzschild radius. The more massive it is, the bigger the Schwarzschild radius, but the speed of light doesn't change. And so the frequency right before the merger tells you how much mass there is. But you can also determine how much mass there is afterwards by watching the thing settle back down, what's called the ring down phase. And so this is a little plot. Again, we're dealing with a tiny fraction of a second here. And when you're doing the in spiral, for example, what the binary pulsar is doing now, gradually getting closer and closer together, you can basically use the post-Newtonian theory. When you get close enough so that you're not really traveling in circles anymore, but you're starting to merge and you're starting to perturb the shape of the event horizon or the neutron star, then you have to use the full theory. And in order to use the full theory, it's too complicated to actually do the algebra. And so you have to do this by computer simulations. And so in the merger phase, as these things are really getting close to each other and touching, the way you do it is you construct a computer simulation of what ought to happen. But then after they actually merge and this ring down is in progress, there's another kind of approximate theory, black hole perturbation theory. So you've got a black hole, but it's a little lopsided. That's, again, something you can do algebraically. So there's one approximation that works out here. There's an approximation that works out here. But in between, when all of the features of relativity are in play, you probably have to deal with it as a computer simulation. One last piece of theoretical work, which is there is this very curious number, which is c to the fifth divided by g. C and g have their usual meanings in this little equation. That's the speed of light. That's the gravitational constant. We've been using these constants all along. And it turns out, each of these constants has units associated with it. The units of the speed of light are meters per second. There's some more complicated set of units for the gravitational constant. But it turns out this particular combination, c to the fifth divided by g, has units of a luminosity. It's units of luminosity. And if you ask, okay, let's do the multiplication, c5, c to the fifth power over g, these are constants of nature. So this is somehow some kind of very special luminosity in the same way that c is a very special speed. And it turns out this luminosity is equal to something like 3.7 times 10 to the 52 watts, a lot of wattage. In fact, it's 10 to the 25, almost 10 to the 26 times brighter than the sun. And this is greater than all of the electromagnetic radiation in the universe put together. So this would be a greater luminosity than the whole universe put together, at least as observed in ordinary electromagnetic radiation. The reason this is interesting is it turns out that this is a maximum luminosity in the same way that the speed of light is a maximum velocity. And in particular, it's the maximum luminosity emitted in gravitational waves of a merging binary black hole. So at the very moment when the two event horizons touch each other, you just for that instant achieve this luminosity. Remember, the brightness of this thing in gravitational waves has been increasing all along. It's been getting brighter and brighter and brighter and brighter, and it gets brighter right up to the point where it hits this number, and that's the moment that it merges. So the reason this is interesting is that this is so bright, that there's so much gravitational radiation being emitted at the point of merger, that it outshines the whole rest of the universe for that one tiny second. And it's because there's so much gravitational radiation emitted that it turns out it's possible to actually detect it if you have sophisticated enough instruments. And that's what we'll talk about after intermission. Okay, so the question then is, how would you go about observing these gravitational waves? The first thing is that there is, as we've said before, a plausible source of these waves that's really expected to be very powerful. We know that there are double neutron stars. That's what the binary pulsar is. We know there are double neutron stars that will emerge in a relatively short amount of cosmic time. We also know that there are systems that contain a black hole, some of which have a large enough companion star, a massive enough companion star, that you expect the companion star itself to turn into a black hole after it undergoes a supernova explosion. An example of this is the famous system Cygnus X1. And so you know that these will evolve into double black hole systems. So we observe double neutron star systems, we observe things that are likely to end up as double black hole systems. We know that if you merge these kinds of things, you get very large amounts of gravitational wave radiation. So there's some expectation that there are sources of this radiation which will produce large amounts of it that you ought to be able to see. So this is what's said down here. Given the huge amplitude of these waves, such systems should be observable, not just in our own galaxy, but in any galaxy anywhere in the universe. And that's important because while we do know about these objects, there are only about a dozen of them in our galaxy. We only expect double black hole systems to be produced, I don't know, once in a long while. These things will merge in a few million years. And so the expectation is that there'll be an event of this kind, a merger of neutron stars and black holes, once every million years or so in this galaxy. So if you're going to be able to see these things, you'd better be looking at millions of galaxies so that you have a hope of seeing such an event once a year or so, because we can't be waiting around for a million years to see these things in our own galaxies. Fortunately, the amount of gravitational waves emitted is very large, and so you do expect to be able to see these mergers at very great distances. And so there are millions and millions, perhaps billions of galaxies in which such an event could be observed. And you do expect to see at least one per year and perhaps more, depending on the sensitivity of the instruments. So what happens when a gravitational wave rolls over you? So we're sitting around on Earth, in the distant universe somewhere, two black holes collide with each other. The black holes emit all of this gravitational wave radiation, some tiny fraction of which reaches us, because it's a 1/r² process, just like light. So when you're very far away, you only see a small fraction of what was emitted, but there was a lot emitted. We're a long way away, but there's still some. So this wave rolls by us. And what happens as that happens is that the curvature of space-time changes, and the sizes and shapes of objects are changed periodically. And this is represented down here. Here's the wave over the course of one wavelength, basically. And you can imagine this wave is moving from left to right. And as it does so, it passes over some object. And what happens is that as it passes over, the object gets squeezed first in one direction, then in the other direction, then in one direction, then in the other direction, as the wave passes over it, as is indicated here. So the plan is that you want to be able to measure the length of something to incredibly high accuracy, because by the time this gravitational wave, this curvature reaches the Earth, although it started out very powerful, it's a pretty small effect, and so this down here is greatly exaggerated. The effect is small even compared to a single atom. So you better be able to measure the length of something to super high accuracy. But if you can do that, you'll see it going back and forth as the wave passes over. The exact effect depends on the orientation of the length you're measuring compared to the direction of the gravitational wave. If it's coming sideways, you'll see something like this. If it's coming from out of the plane into the paper there, you'll see it move. You'll see it stretch and decrease in the other direction. So it depends exactly on the direction that the wave is coming from. And something that's important to keep in mind is that you're not looking for a one-time effect. You're not looking for this thing to suddenly get bigger or suddenly get smaller. What you're looking for is a very specific and well-known pattern of changes. It's going to do this, and the thising will get higher in frequency and larger in size as time goes on, because you're looking for a chirp. And that's important because, you know, any instrument that is likely to be able to detect this will also be sensitive to earthquakes, to a truck going down the road 30 miles away, and things like that. And the way that you prevent yourself from being fooled by terrestrial events is basically to look for this particular pattern, the chirp, rather than simply a slight change in size. So how do you do this? We know how to do measurements, high accuracy measurements of lengths of things. They knew how to do this in the late 19th century. Michelson and Morley did it. You do this with an interferometer. Remember the setup for the Michelson-Morley experiment. They figured this ether wind was coming down here, and so they wanted to compare the distance from the beam splitter here to one mirror, as opposed to the distance between the beam splitter and a different mirror. And you do that by sending the light in these two directions, recombining it, and seeing if it recombines as constructive interference, where the peaks line up with the peaks, or destructive interference, where the peaks line up with the troughs, and you cancel the light out. So if you were to do this in such a way that rather than just sending it up once and bouncing it back, you send it up and bounce it back thousands of times. If you do it that way, then a change of 1/1000th of the wavelength changes you from a peak to a trough. And so if this distance were to change by 1 part in 1,000, you'd be able to see a change from destructive to constructive interference if you bounce the thing back and forth enough. It turns out you can also detect very small changes. You don't have to go all the way from purely constructive to purely destructive interference. You can change just a tiny little bit, make it just a fraction more destructive, and the light will diminish very slightly in intensity. But we've gotten really good at measuring how bright light is. That's what cameras do, is they measure how bright light is. We have very high-powered optical detection equipment. And so by combining bouncing the light up and down a large number of times with a situation in which you can detect a very tiny change in the interference pattern, you can have a situation in which you can measure changes in the length between the beam splitter and the mirror to incredibly high accuracy. And in particular, you can compare it to the length in the other direction. And so they figured it out for a merging stellar mass black hole in a distant galaxy, you better be able to observe changes of 1 part in 10 to the 21 of the length. So if you have a kilometer-long path, if the distance between the beam splitter and the mirror is a kilometer, then that's about 10 to the minus 18 meters, which is a small fraction of an atomic nucleus. Now, you would think that measuring something to 1/1000th the size of an atomic nucleus would be very difficult. And you would be correct that it's very difficult. But it turns out that with this kind of a laser-driven interferometer, the technology was developed over the past few decades good enough to actually measure a change in the length that small. That was a tremendous technical achievement, but it has indeed been achieved. And so here's what this laser interferometry gravitational wave observatory looks like. It's basically 2 long tubes, 4 kilometers as it happens. They're set up at right angles to each other, and it works just like Michelson and Morley had it, only with an additional century's worth of technology. So you send in laser light, you pass it through a beam splitter. Some of it goes this way, some of it goes that way. It bounces back and forth for a while. Then you recombine it, and you have a detector out this end, which measures to very, very high precision how bright that light is. We've constructed 2 of these things. Actually, by now there's a third and a fourth coming online. The first 2, one was in Louisiana, the other in Washington State, so a couple thousand miles apart from each other. The point of having more than one of these things is that it helps you filter out local events, little local earthquakes or trucks and other kinds of local events, because you are looking for chirps, and you're looking for identical chirps in 2 systems 2,000 miles away, because if there's going to be a gravitational wave passing through the Earth, it'll pass through both Louisiana and Washington, and indeed everywhere else on the planet. There'll be a little bit of a time offset by a couple of milliseconds. Why? Because it takes light a couple of milliseconds to make it from one place on the Earth to another, and this wave is propagating at the speed of light. So there may be a time offset of a few milliseconds, but other than that, you're looking for identical chirps in 2 places. By now, as I said, there's a third online in Italy. 3 of them is good because the time delays between them allows you to triangulate the position that the gravitational wave was coming from. There are more in construction. There's one that's going to come online in Japan. There's one that's going to come online in India. And all of them are being constantly upgraded so that they're increasingly sensitive as time goes on. So here's what it looks like. These things actually exist, amazingly enough. Here's the one in Louisiana and Livingston. Here's the one in Hanford, Washington. You can see the difference in the vegetation of those two places. And they have been in operation now for some number of years. And in early 2016, so just under 5 years ago, they announced that they had indeed discovered a gravitational wave, presumably coming from a merger of 2 black holes that had passed through the Earth. The observation was made on September 14th, 2015, and then they spent a number of months making sure that they hadn't screwed up in some way. And here's the data. Notice down here, this is time in seconds. This is 2/10 of a second from the start of this plot to the end of this plot. So this is the 2/10 of a second where we are observing the merger of 2 black holes. So, and this is strain. That's basically how much the length has changed as a fraction of the length you're observing. So you're observing 4 kilometer thing, and so the change in the length of the thing between 0 and 1 is 10 to the minus 21 times 4 kilometers. So this is some kind of delta factor, and it gets bigger and it gets smaller. So this is how it is ordinarily, and it gets bigger and smaller. Here's what they saw at Hanford, and this orange spiky thing is what they actually observed, and the yellow line drawn through it is a prediction of one of these computer simulations of black holes merging together. So similarly here in Livingston, Louisiana, the fat blue line here is the observations, and the thinner blue line is the prediction made by one of these computer simulations. And if that wasn't, and notice what's happening. The waves are getting closer and closer together and bigger and bigger, just like they're supposed to, just like a chirp. And if the comparison between theory and data wasn't enough, what you can do is take the Washington data, shift it by a couple of milliseconds, and put it on top of the Livingston data, the data from Louisiana, and they lie right on top of each other. And so they had this fabulous press conference on February 11th, 2016. And I have to say, I saw this data and the hair went up on the back of my neck, because this is just like it looks in the textbooks. It's unbelievable. I know I wrote such a textbook, and this is figure 9.3, in every textbook on relativistic astrophysics that's ever been made. And here it was come to life. And the implications of this and the subsequent observations that have been made since then, there are now dozens of these kinds of objects observed. That's what we're going to talk about in the next lecture.